All right, desperate times call for desperate measures. At least we'll get some audio this way. All right, so as usual, we're going to start with a little bit of review, talking about the content that we talked about last week, namely sensors and the output types and input sources between them. Okay, so remember, new keyword, if you guys haven't learned it before, is a transducer, which is, again, a clever device that is taking advantage of some facet of physics or chemistry to turn a characteristic that we're interested in, the presence of some sort of gas or the flow rate of a liquid, for example, and it turns that characteristic into electricity. There's lots of different ways to do that, hundreds to thousands, but we covered just a few. But there are two domains. Again, I really want you guys to understand this, that there's the analog output and the digital output. Okay, a lot of people get tripped up on the digital part of this, which they take to mean that, you know, when I ask you if a device is digital or analog, they kind of think, does it have a computer in it or not? That's not the correct heuristic. That's not the differentiator here. It's whether or not it's just can output, is there something or is there not something, and then that thing changes, or how much of that thing is present at any given time, okay, across a scale. So this would be our analog. Okay, analog temperature sensors, some sensors, analog sensors would be like temperature or pressure or humidity, right? Flow rate, density, right? These are all numerical values that they can go from almost nothing at all to some arbitrarily high value. Right, and the change across that difference matters. Okay. Digital outputs would be like our beam break, right? Like our limit switch. I would accept a temperature sensor, but you would have to have a lot of text beside that temperature sensor that says, like, with thresholding, before I would consider that to be a digital sensor again. If I asked for different types, right, analog versus digital. Another digital output would be like a float switch. Okay, so we're measuring water, you know, like a flow switch would measure water, but this is an analog because we're measuring the amount of flow. Where a float switch, you know, we might be measuring how much of a liquid is in the tank, and that is some amount of liquid, right? And we figure that out by precisely putting our floater where it needs to go so it trips when it needs to trip, right? So in that way, we are keeping a certain amount of water in this tank, right? X liters of water, but that's still a digital sensor. The output that the sensor outputs only can really have two states, low or high. That's what we mean by digital. Okay. Again, I know this is not the first time I'm bringing this up, but it will probably be the last. I just wanted to bring it up because it is a complicated topic. The idea of digitizing an analog signal. Okay. So again, what I mean by that is that in real life, we would expect even a sensor that we design, right? The output of a sensor that we design, ideally, would have a super straight output, right? If this is temperature, and this is voltage. All right, there's a couple things to understand. One is that as we would hope that this is linear, right, that this is a straight, super clean line. Okay, but reality is a little bit different. This line will be like that, except that it'll have some variation, right? Random noise will be in there. The sensor will be a little bit off. Pressure will be changing a little bit and messing with us. Okay, we'll have a little bit of fuzzy variation in that signal. Okay, so that has a couple of implications. One is that our signal will never perfectly be accurate, right? If this should read exactly bang on at 5 degrees C, this might read 5.1 degrees C 1 second and 4.9 degrees C the next, even though nothing actually changed. Okay, the idea that this is an analog signal is that our device, our sensor, is generating a voltage as stable as it can, as accurately as it can, but there's still some variation to it because it's outputting a voltage on a wire, and that output, that voltage, can be changed by outside disturbances. Okay. So all that to say that when we bring in an analog source of data, okay, this signal, however fuzzy it is, okay, in the real world it would be quite fuzzy, meaning that the data would be jumping around a lot of high frequency noise. How do we bring this into a computer and make this meaningful? Okay, because again, this is a voltage on a wire. It has meaning to us when we measure it. When we put a multimeter onto the copper and we turn that into a number, it's like, okay, that means something that's useful. So to get that into a computer, we must do something called a analog to digital conversion. Okay, an analog to digital converter is inside of our PLC's computer. And again, there's literally a chip inside of the device. Okay, that has one of these pins. And what it is doing is it's taking our variable input signal, like that, and it's chopping it up into bins. Okay, so we start to get an approximation of that signal. I guess it would kind of go up a little bit like that. Okay, it'd be the same time scale, it wouldn't be stretched out, but you guys get the idea. Okay, so that's kind of what it means here. And the number of bins is our number of our resolution. Okay. So the finer we make these squares, the closer we can approximate our signal and the less error there is in our input. We're not changing what we see quite as much in the number that we end up reporting. Okay, so what this is this gives us a number. This number is really just the number of bin that the signal is at any particular time. Okay, if our signal could be a maximum of 0 to 100 bins, right, where the difference between one bin and another bin is 1/100th of the maximum, like that, we just refer to it as the number of bin it's in. So if it's in the 100th bin, then it's here on the signal. If it's in the 50th bin, it's halfway up, and 0, and so on. And then we just record, and each time slice over time, we say, hey, sensor, do an instant digitization. What is the voltage on this pin now? And it, boom, it goes, it is in bin 2 out of 100. It goes, okay, thank you, that's in bin 2 out of 100. One more loop, okay, what is the voltage now? And then it's, oh, we've raised one, it's now 3 over 100. Okay, and then we just keep doing that, acting on the feedback, and proceeding accordingly. So this still gets us some useless unitless number. Well, it's not useless, right? It's still qualitative. We can see this digital number going up and down, but it doesn't really mean anything to us. We know that this is 0 to 100, and we can look up from our temperature sensor, for example, or even experimentally determine, we freeze it, we put it in a freezer that we know is at 0 degrees C, and we see what number that is, and then we put it in a boiling hot thing of water, 100 degrees C. What does that come up to? So this might be 2, and this might be like 80, and we know that 2 is 0 degrees, and 80 is 100 degrees. Okay, so last thing, again, I'm gonna touch on this one more time, is the idea of a calibration. We haven't really gone over this in these exact terms, but I'm gonna describe it as 1 and 2 point calibration. Okay. So what we're actually doing here when we calibrate our sensor this is our temperature scale, and this is our voltage scale. We're saying, or actually, this would be our unit, right? 0 to 100. So this is 100 units, and this is 0 units. This is 0 degrees C, because we can go negative, right? This would be 100. Okay, so we're saying at 0 degrees C, we're at like 2 units. We're at 2 units. What? This is a brand new marker. How is that possible? We're at 2 units. Okay. And at 100, I said we were at 80 units. Okay. So now we know that assuming the relationship is linear, that the output is linear as opposed to non-linear, which is a big if, by the way, because the design of sensors, a big design point of engineers is to make the output straight. A lot of times it won't be straight, it'll be non-linear. You'll have this weird curve, and so a straight y equals mx plus b won't get you a good calibration. You would have to have a complex curve that you could fit to this curve and then look up essentially at every point and correct for it. Anyway, once we have our calibration curve, we can turn our unit into temperature, right? That we're essentially saying for each step of temperature, how much is that in change of voltage? Degrees T versus degrees V, or sorry, delta V versus delta T, right? You guys will understand that this is the slope of this line. Okay, so now, magically, we can programmatically turn our unit into something that is meaningful in our society, right? Degrees C in this case. Okay, but this is something that we typically have to do every time. Okay, when you have a sensor, whether it's pressure or temperature or humidity, it will always give you, you'll always kind of have to go through this. You have the raw reality of the sensor type, you know, digital output or analog output, and then it's going to be digitized. So you're going to bin it between 0 or 255 or 0 and 65535, right? And those steps mean something. Then you would have to look up in the data sheet, okay, what does how much voltage change mean for how much of that characteristic, right? And then you would either look up on the data sheet, it would give you, okay, this much change in voltage means this much change in the thing that you care about. You can program it in that way. Or you could test it. Like I said, you would have an environment, you would have like a calibration gas that was at a certain concentration or a flow rate that was like calibrated and known to be going at a certain flow rate that you could turn on and off to calibrate yourself against, all that good stuff, okay, where you could teach your system to be accurate, okay, because that might be important. You might be tasked with something like, let's keep the flow rate of, or set an alarm if the flow rate goes under this or over this. And you have to be numerically accurate. And it would be up to you to implement, the 2 or 3 lines of structured text that it would take to do that, to grab the reading from the input, to massage it into an actual reading, and then to do something with that output. Any questions on that topic? Cool. All right, so I know I've been reviewing that one a few times, but this should be about it right here. So on the final, I'm going to ask you to list digital sensors, analog sensors. What is an analog and digital signal? Please get that one right. I'm begging you, please. A few more good things to know, right? Stuff that'll come up again in a conversation or in the workplace or whatever. Okay, one is the idea of capacitance and how we measure capacitance. That really is that capacitance can be thought of as a charged plate. Okay, that electrons, a bunch of them, are on the negative side, right? Electrons are negatively charged, so there's a lot of electrons piled up over here, but there's relatively few over here. Okay, there's holes for electrons. They want to be here. There's an absence of electrons. And right here is a really thin layer that's preventing these guys from just jumping across, okay? This is a capacitor, that it's 2 charged plates where electrons could exist or not, and a really thin layer separating between the two. All right, 2 things scale with capacitance. Distance is related to capacitance. The closer these plates get, as they get like infinitely closer together, the capacitance starts going up. Same as if they're farther away. When 2 plates are farther away, the capacitance goes down. Same deal if you misalign the plates. It's all kind of like relative surface area. If you misalign the plates, the capacitance will go down too, because less charge can see each other, right? The distance here that the electric field has to cross is greater, okay? So distance and capacitance is related. The other thing is pretty much what I just said, which is surface area. So surface area is also linked with capacitance. If we had really big plates, okay, this is literally a small capacitor versus tiny wires and very large plates. This would be a much better capacitor, assuming the distance is the same between these 2 plates, than this one. Okay, more plates is more electrons can fit onto those plates within that capacitor, higher capacitance. Okay. Sensors that are capacitive in nature, for example, microphones, all they do is look for a change in capacitance. Okay, so for example, a material that is deflecting, like this, even if it's not a piezoelectric material, or actually, let's do it where it literally is a capacitive sensor. So one example of a microphone, I believe this is called an electret microphone, is that we have a hanging eardrum element here, okay, literally like a drum, so sound waves come in and they will deflect the drum, just like our eardrum. And then attached to that eardrum is one side of our plate capacitor. And then the other side is just rigid, it's attached. You guys can see here that as our eardrum goes in and out, as the sound waves hit it, the distance in between these 2 capacitive plates will change, right? The capacitance will change as a result. And what we can do is we can sense that change in capacitance. But again, change in capacitance is tricky, right? Change in resistance is relatively easy. We can get that with our resistive divider, our potential divider, okay? Where if this resistor were to change inside become more or less resistive, our voltage would kind of automatically change as the ratio between these two. Nice and easy. But in order to read our capacitance, so the capacitance changing is all well and good, but the thing that our system actually needs is voltage, right? That's the thing that we can digitize and pay attention to and actually use in our system. So in order to do one more step to change capacitance into voltage, we need to really kind of understand what's going on in this capacitor. And there's a couple of ways of doing that. One is that we could charge the capacitor. Okay, so this is voltage, and this is time. If we suddenly charge the capacitor, and then take away, the thing that's charging it, for example, if we charged it with the battery, if we just took away the battery and let it discharge, it would slowly discharge kind of like this, right? The voltage would kind of curve, and then it would maybe level out like so over time. So what we could do is we could charge it, we could turn on the source, with a transistor, and then wait some number of milliseconds later. Boom, check in again. What voltage level are we at when we check in this number of milliseconds later? And the interesting thing is that if there's more capacitance, it won't decay quite as much, so it will be this much higher. If there's less capacitance when we check in at that time, we'll have decayed more quickly, and we might be all the way down here. Okay, so that is the voltage change when we check in. If we check in here, it might be like 4.2 volts. If we check in here, it might be 3.8 volts, so on and so forth. Okay, so that's how we can turn a capacitance. We're testing this capacitor, the discharge and charge rate of this capacitor, just the discharge rate of that capacitor, in order to then understand the capacitance of it. Okay. There's one more that we didn't really go over in terms of like how we actually use it, like we did here in capacitance, but still the idea of an inductance sensor, an inductive sensor, is also something that I want you guys to understand. Okay, remember that an inductor is a coil, a solenoid, that we are running current through. Okay, as we run current through this solenoid, it forms a magnetic field. We're storing energy. It's almost like we're storing potential in water. I like to think of it like rushing water, right? Water has gravity to it. It has momentum and inertia. If we were to suddenly cut off the current of water, that would still have some amount of force to it. It would slam, right? So that's almost what I think of. It's like the energy is still there from the current flowing. If it were to suddenly stop it, that energy would have to go somewhere. And that's very similar to how inductors work. You should know that inductors, or the idea of mutual inductance, is that if we have two coils next to each other, okay, if I pass current in here, and there's really good coupling between a coil very close by to it, like that, then we will see current flow here as a result. Okay, we'll kind of couple current. There's a couple things that this scales with. Like capacitance, it also scales with distance. So inductance is L, actually. But so if we were to, smush these coils together or bring them apart, that could be one way that we could change that. Another is the idea of magnetic permeability. Okay, for example, we could be measuring the air in between two coils and how that changes. The presence or absence of different gases or radiation or metal. All right, for example, one way that metal detection is done is that we have a coil that's energized and we're just running current through all the time. When we're in the presence of a ferrous metal, metal has a higher magnetic permeability than air, which means that the inductance of our coil suddenly goes up. It becomes a better inductor when there's iron nearby. It can store magnetic energy more easily. Okay, it's like a booster for magnetic storage. Okay, so that metal, the presence of that metal, we could see as a signal, right? As a rise and fall in inductance. And then we can change that inductance to a rise and fall in voltage, and now we get metal detection. Okay. The other practical example that I see all the time, I think about it every day when I'm driving, is sensors that can tell when you're stopped at a stoplight are based on induction. They work by, if you guys ever see the busted up section of concrete, it's usually in kind of like a patch, like a square patch. There's because there's a big old coil in there. Big old coil. And all it's doing is there's some low amount of current that's running through here. Okay, it's doing its thing. And when there's a presence of a big block of metal, okay, a big motor, big car chassis, a big scooter or whatever, then it couples to that. This big coil becomes a better inductor. Its inductance goes up due to the presence of the metal above it. And the system can see that change. It can detect that your car is there or not. There's actually a trick that smaller vehicles, some people have really small scooters and stuff, they put large metal blocks and magnets and things underneath their scooter, and then the system can see them. So fun facts for inductance sensing. All right, and then the other example that I gave for the capacitor is how your touch screens work. Right, so again, they used to use resistive touch screens, which pretty much just registered where on the screen two pieces of film intersected, where one could tell where you touched on the Y direction and one could tell where you touched on the X direction. This one's similar, except it breaks up the phone into a group of cells, and then each one of those cells is charged just like we talked about before. So for a given one of these cells, over time, maybe 100 or 1,000 times per second, it will be charged up, and then it'll decay over time. Then the microcontroller will time it, or it'll charge it, and then it'll check in at some point later and see where it comes in, on that line. And then it'll look, okay, here is where it should be without a finger being pressed. When you turned on your phone, you calibrated it to a blank state. The dust that's present there, the oils that's present there, the charge of the air, all of that stuff goes, okay, we expect that to be here. It does that 1,000 times a second, and then when it sees that it is significantly different from that calibrated state, it registers a touch to the controller, and it turns it into a digital signal, right? Because this is 1,000 potential squares that says, no, there isn't a touch here, 0, 0, 0, 0, 0, 0, 0, 0, and then this is our 1. There is a touch here, registered in this pixel position, blah, 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 tell it to the OS. Okay. All right, so ran short of time last time. I actually need to run out a couple minutes early today to pick up my dog from daycare, so we're going to get that time back, at least today. But I did want to go over some really cool sensors that we weren't quite able to cover last time, because I think they're really neat and they are everywhere, but people don't really realize it. This first one is colorimetry or colorimetry, used in lots of different ways, and there's a couple different ways of doing it as well, but I just thought it was worth mentioning. The first way of doing it is similar to a spectrophotometer. Okay, this is that we have a white light source, and then it goes through a prism. So light goes in here, and then it shoots out and gets linearized down into its component parts. So this would be red, then you would get kind of orange and yellow, green, so on, blue, finally until UV, until it's not visible anymore. Okay, but it spreads it out into this spectrum. Okay. Cool thing happens. Now we can now expose a sample of something just to this specific light. Okay, so if I have a vial of some unknown liquid, okay, some pond scum or whatever, I can expose that liquid to very pure blue light. Okay, it was white light, but we filtered out everything but blue light. Okay, we're just seeing how it responds to blue light. On the other side, we have a photodetector, right? So this is a photodiode, and then this is a photodetector. Okay, so we're counting, the number of photons we see. We know photons in, so we are putting in this number of photons per second, and we are getting out this number of photons per second. Okay, so based on in versus out, we can see the optical density of this sample in response to blue light, for example. Okay, what we do is we chart that intensity, that response, how well it passes or reflects that light for each of these bins. Okay, this is how well it reflects red, this is how well it does for orange and yellow and green and blue and UV and so on. Okay, and this gets us a spectrum. Really cool thing is when you make this curve, when you chart this curve like so, you can classify materials like this, that their spectrum will come up in a very standardized, understandable way. Okay?
How they find the compositions of stars and planets?
Yes, very similar. Yeah, that's called chromatography. Yeah, photochromatography, I believe. But very, very similar. Yeah. So we can keep track of chemical processes this way. We can do like food science, different chemical indicators will change spectrums, all kinds of stuff is essentially related to this idea of create a wide array of light, filter that light, and then see how much comes through. Okay, the other way of doing it is similar, where we have a white light emitter again, but rather than filtering that light, right, we don't have a prism this time, we just pass it straight through our sample, but then our photodetector is the thing that is sensitive to different wavelengths, where we would have like a red detector and a green detector and a blue detector and a yellow detector and so on and so on and so on and so on. Okay, that is another way of doing color detection, right? We're essentially just detecting color, changes in light intensity versus light. Only thing is that we can't really get as good of a spectrum as this, right? This is actually a continuous spectrum. We could sample this a million times, a million changes in color from red to the UV, a million steps and change. But we can't easily have a million different diodes that are sensitive to a million different frequencies, right? So instead what we do is we just have three. We just have the red, green, and blue like our eyes see. Even humans just have red, green, and blue cones, okay? Sensitive to color, or rods. I don't remember which cones, I think. Anyway, we just have these three, and then we can see that based on the intensities of these three wavelengths, we can get a similar color profile, okay? And that is just, in a nutshell, how colorimetry works in industry. Like I said, lots of things, literally sometimes producing paint, right? You want to have a very specific color of paint in your industrial process. And your PLC might be tweaking the amount of ink that goes into that paint, or the amount of white versus the amount of gray. I don't know if you're trying to dial it in, right? So some part of your process may very well be an outcome, a spectrum, an intensity that you'll have to keep an eye on while you're monitoring your process. Okay. All right, this one is worth noting again because it is really everywhere. IR sensors, also called PIR sensors. I'm starting to lose numbers, I don't quite bad ones. Okay, so PIR sensors will often work how this one works. So like lights that turn themselves on, for example, when we walk into this room, if you guys have ever done that, the lights come on by themselves. That is done with a PIR sensor. And really all it is one or more photodiodes that are all kind of looking maybe in 3 different directions that are very sensitive to IR light. Either there's a filter here preventing any other kind of light from getting in, or there's a coating on the diode themselves. There's something that is filtering out all light but just infrared light. It's the far band. So blue is gone, UV is gone, everything but red. Okay, so we, as humans, we glow all the time, even in the pitch black, in the IR band. Okay, if you eliminate all color except IR, and you have something that is still sensitive to that kind of light, we don't have cones in our eyes that are sensitive to IR. The cones in our eyes kind of look like this. There's a little bit of crossover between green and blue, and then there's a sensitivity of red. Okay, this is the red. But IR would be like this band. It starts here. Okay, so all the light, we could be blinded by infrared light. If there's a strong laser or a solar flare or something, we could never even see it coming. Our eyes would be boiled in their sockets, but we would never see a flash of light because it doesn't trigger our sensors. Okay. However, if we did have proper sensors, we would see each other glow in the dark. Our bodies release photons in the infrared band, and PIR sensors are sensitive to that. Okay, so they're calibrated to what does a dark room look like. You know, it'll have some amount of IR in it from the equipment and the HVAC and whatever. It's like, okay, this is what an empty room looks like. We get some probably voltage from that, right? The difference between absolute zero, this is called the dark current, and probably like an actually dark room is some amount, right? And then when a person walks in, we will see that jump, right? It's probably really high as they walk through the door, and then raised probably a little bit through ever after as they continue to inhabit the room. And that's something that we could see, that's something that we could detect. So we would do something where we either set a trigger where we look for this high point, right, for it to cross that threshold right there and then turn on the light. And then as long as we are above our dark room currents, we keep the light on, right? Or maybe we always look for this and we just keep it on for an hour and then we wait to get triggered again. And then if we get triggered again, we keep the lights on. If not, we turn the lights off, however you want. But that is a very common example of PIR. Another example, adds an emitter. Okay, so PIR relies on ambient IR, things that are emitting IR, mainly people and animals, right? But IR, active IR, would swap one or more of these IR receivers for an IR emitter. Okay, so now we have an LED in here that we are sending out photons actively. Okay, so the cool thing about this is that we can see or know how much light this should be putting off and how much light we should be receiving. Okay, so again, we have our baseline, how much should we be receiving? If it's a distance sensor and the thing that we're sensing is infinitely far away, we're probably not going to get any IR back, or we'll expect to get no IR back, right? But if something is right up front, if we're holding a mirror to it, practically, we would expect to see almost the full intensity of that IR reflecting back. And then we can do a lot of interesting things with that. We can do a presence detection, right? Is the hand there or not for sinks and things? We can do distance detection, right? Little robots, seeing how close they are to walls. Or Roombas actually use this for fall detection, okay? As they're approaching a step, the reason that they don't fall down the stairs is because they are putting out a stream of IR light. And it can see whether or not that gets bounced back by the floor that's underneath it or not. And if it sees that it's not getting that light back, it's being projected into nothing, it's looking over a stair step, and it shouldn't continue in that direction. It should turn back. And again, that's another complicated thing, that it is a analog signal. How much light are we seeing at any given time? Right, that is a scalar value that's varying from 0 to 100% intensity. But maybe the thing that we actually care about is just when does it cross some arbitrary threshold, right? And that threshold is the thing that's actually meaningful. So that typically is like the extent of the complexity of your PLC program. That all you'll really worry about or care about is, okay, in this analog signal, how do I establish this threshold to do the thing that I want to do when it needs to do it? Okay, and that it does that reliably and that it doesn't mess up and it's accurate and all that good stuff. Okay, so that's IR sensing. Any questions? Cool, good stuff. Okay, last one for the sensor review, anyway. Particle sensors are really cool. This is how smoke detectors work. This is how dust particle detectors work. This is, in some ways, how X-ray Geiger counters work. A little bit different, but they're technically still particle counters. Okay, so the way that this actually works is that most particle counters will actively have a fan running through them to push air through. You have an air inlet, and then it channels down into a very small channel. So here's our laser source, our photodiode, that it looks to see a very small part of the tube that's flowing through. Okay, so it reduces it down, way, way down, so that a lot of our particles will travel through. Okay, and then it blows up. So if something as small as a micron passes through here, it will make a really big shadow. Okay, we'll see the intensity of the light go from really bright, it'll peak down to really dark for a second as the shadow of the dot passes through our detector, right, the speck, and it will keep on going. So a larger speck will cast a bigger shadow, it will get more dark, and the smaller speck won't cast quite a big shadow. We might only turn a little bit gray as it passes our detector. Okay, so we count the spikes and we can count the number of particles that pass per second. And if we count how big the spike is, or sorry, we register the intensity of that darkness, we can see approximately the size, right? Where like a particle that's this big would make it this dark when it passes, and a particle that's this big will make it that dark. And so some things, for example, we figure out that the particles that make the detector this dark make people sick, or trigger people's asthma, for example. So PM 2.5, particulate matter in the 2.5 micron range, micrometer, is important for environmental monitoring. and detection and job site. Like construction sites that make a lot of dust are required to have their PM 2.5 values be within some range. So they have to have detectors, they have to have personnel on range, they have to have safety and PPE and all that good stuff. Smoke detectors too, right? As smoke essentially is just particulate ash in the air, carbon, right? Suspended in the air. So the difference between air that's filled with particles and the difference between air that's not is differentiable. So we can train a detector that when we have a sufficient number of particles in the air of a troubling size, trigger an alarm. And that's really what a smoke detector is. Okay. And again, whether it's light or whether it's radiation, the thing that we're sending out and receiving on the other side doesn't really matter. Depending on the application, it can be different, right? Whether you're measuring radiation or smoke or particles or whatever. Okay. All right, so this last one I didn't get to last time, but is definitely relevant in our current day and age. It's that a lot of industries will have some computer vision component that at the very end of your production line, you make your circuit board, you make your gadget or gizmo, you're going to have quality assurance checking that it was made correctly. So really what it means for PLCs and industrial systems in general, it just means that at a certain point on the line, you'll have a black box that has a flag on it. That flag says good or not good, right? And that can be an incredibly complex process. This is like the epitome of an analog into digital thing where we have a sensor that is taking a million measurements, right? 1,000 pixels by 1,000 pixels, and it's getting an RGB value for every one of those. And then it chugs it through a computer that crunches terabytes of information. All of that to just have a flag that says, are we good? Yes. Or are we not good? No. And a PLC could be plugged into that flag. That there's a computer, right? A high-powered computer that's running this AI model, whatever. But all it's doing at the end of the day is toggling a line high or low, and then our PLC will react to that, right? Do we need to kick a product off the line? Do we need to sign an alert? Do we need to change something about that process, like make heaters more hot or whatever? Okay, that AI and computer vision would be a step in that process along the line, a black box that would be a potential input for our PLC. Okay, so that's something that could happen too. All right, so no questions? No sensor questions or nothing? Okay. Guess that killed a good hour, right? Do that 1.5 more times. So, today's topic is the Internet of Things, in part. Not only this, but that is to say, lots of different devices at different places in the network and in space that are all talking to each other, right? They're all communicating data to either each other or to a central point, like a server, for our use, essentially, for our convenience, for our efficiency, whatever, the betterment of some kind. So the term itself, Internet of Things, is kind of a catch-all, but really it just means that devices that can transfer data. Okay, it doesn't necessarily have to talk to the internet. Okay, like an Internet of Things device could just have a long-range radio in it, right? It couldn't maybe necessarily actually be able to like go to a website or bring up a browser, but it could send information off that could be received by another device that could then put that up onto the internet, into a database somewhere where a server could query it and put it into a graph or into a report, right? So that's kind of like the things part of Internet of Things. People will often think of things like your refrigerator or your coffee maker or that kind of silly things, but in industry it's much more useful things like where's the stuff, asset tracking. You can actually see it travel along the route from A to B. Is it the right temperature the whole time as it's traveling? So cold chain tracking is a big deal, right? For pharmaceuticals, if you want to make sure that your drug was never warmed up and spoiled, you could ship it with a tracker that lives on the carriage, on the train. You could see where it is at a given stop, the temperature over time, and all that is reported in a handy little dashboard, right? You never actually have to send someone out to that carriage with a checkbook or with a clipboard. The device could just shuttle that information up from the safety of your office, right? So that's asset tracking, that's environmental tracking, like pressure, temperature, humidity, that kind of thing. That's process management, understanding what your machines are doing at any given time, if there's any errors or alerts or if anything's out of whack or out of spec, all that can be reported over the Internet of Things. So there's a lot of complexity with any one of these tiers, right? You have to have the thing to begin with, right, which is kind of a small marvel in itself. That's our microcontroller, right? The thing that used to be the size of a whole room is now could fit in the small palm of our hand and last for a week or a month or a year in a field somewhere. It has a radio in it. That radio has to be able to talk to a base station. That base station needs to be able to talk to a router. That router needs to be able to talk to the internet. The router needs to be able to talk to a server. That server needs to be able to talk to other servers and the ISP, and on and on and on and on. So the complexity really explodes as we go from the device itself to our networking and uplink infrastructure to the back end services that actually host our application and crunch our data, to the data center and materials and things that all this stuff is actually running on in the so-called cloud. And all of this has to talk to each other, and it has to speak the same language or 6 different languages, as you go from point to point. And it all has to work flawlessly and reliably. It's kind of insane when you think about it. But we're going to learn the gist, the tippy top view of what it's like to work with IoT devices. All right, so the first thing that we're going to talk about is the idea of system architecture. When you have as many capabilities as we do these days, there's a few different ways of going about things. We've already encountered one of these already, which was how do we create a PLC system? Okay, because for example, there's an idea where we could have a master controller, right? This is our main PLC, and then this master controller would talk to all of our end devices, where it would spider out, it would talk to all of these end devices, right? So this one PLC might have, one crazy long program that does crazy complex things with all of these different front ends, with all of these different devices. Or we could have one PLC that talks to other PLCs that kind of split some of that complexity, right? And each of those would talk to an actual end sensor. So this main PLC might just have, a little small maintainer or manager role, and then each of these PLCs would be responsible for the nitty-gritty of, here's where you move the robot arm left for 80 milliseconds, up for 90 milliseconds, down for whatever, right? All of that brunt work gets done with these slave PLC, right? So that is one way. This is system architecture in a nutshell. Someone has to decide, okay, this PLC does these things, or this PLC talks to these other PLCs to do the thing. Right? This one might have more cost, but it might have lower cost but higher complexity. This one might be higher cost. You're buying more PLCs, but it's easier to maintain and it may be more of a reliable system. Okay, all things to keep in mind. So we have a building of complexity. We have devices talking to other devices, talking to other devices that are all kind of daisy chaining up or rallying the message up the chain. Okay, so at the bottom of the chain, we're talking about the things in the Internet of Things. Okay, these are the sensors, ideally, or actuators, right? That's kind of like the two things that you can kind of have. You can kind of have sensors, where they report information about the world, and you can have actuators that will do something to the world. Right. And you have a device that can either read from or write to one or more of these things that can do either one or the other. Okay, so that's at the bottom of our chain. Now we have to get this data either to this chip so it can, fire the motor, or from this chip so it can report its information. So we're sending data up or we're getting data down. How we do this is another implication. Do we use a wire? Do we go wireless? If so, what protocol do we use? Do we use BLE? Do we use Wi-Fi? Do we use LoRa? Do we use Zigbee? What do we use? I2C, SPI, UART, all that jazz. That is getting the data out of our chip and starting to get it into the system. Okay, typically, this is done by wire, either TTL, that is our 0 or 1, that is our analog signal, that is our UART control. Oops. 1 0 1 0 1 0 0 1. Okay, so now we've digitized our signal and we need to get it out up to the internet. So we do that with a gateway. So we have either wired, so we would do Ethernet, TCP/IP, or we would do wireless, which would be Wi-Fi, or Bluetooth sometimes, or LoRa sometimes. I keep saying that, I'll get into that in a little bit. But essentially a radio signal that carries that information out and is received by a gateway. It's another little device that lives on the premise, but it has a larger antenna on it than our sensor typically. So it has a really big range that it can receive information over, and it can receive from lots of different devices. Okay, so we can have one gateway, and we can have dozens to hundreds of devices that all call back to home on that one gateway, that all receive information to that gateway. So this is, in your house, your router or your modem. This is your internet gateway, as it is. Okay, it turns your Wi-Fi signal to each of your devices, even Wi-Fi sensors, and it turns it into LAN, actually TCP/IP. So this bridges it to a landline connection. This would either go to, like I just said, TCP, IP LAN, Ethernet. It might go over cellular, right? If you're in a field somewhere, cellular. If you're in a field somewhere and there isn't a landline anywhere, you might have to shuttle that over cellular. If you're really out in the boonies, you might even do satellite. Okay, I've done a couple of satellite contracts too, where they were really out there. They were actually on a shipping container, and they didn't even have cell out there in the middle of the Arctic, but they still needed to get cold chain storage information up to their network. So they did satellite backhaul instead, where they had a gateway on board that could talk Wi-Fi or BLE or short-range radio, right? To get those the short hop from those devices to the gateway, and then backhaul, upload to the internet. Okay, so that would be the stage 2 of our system, kind of the aggregation method. Okay. I guess here's a good time to talk about as any on what LoRa is. So LoRa, it's kind of a funny acronym. It stands for long range. Long range. Not even kidding. And it's spelled like this, with the L and the R. And what it's really good at is it's kind of like cellular. It's actually at the similar radio frequency band as cellular, but you don't need a tower. Okay, so a cell phone to a cell phone, just a very small device, can talk to another device about a mile away. Just like in your hand to another device that is also in their hand. It's about a mile, maybe even 2 on a clear day. And it uses very, very small amounts of power, but the downside is it can move extremely little amounts of data. We're talking like less than a tweet amount of data. So we can say, my current temperature is this, really well. It's great for that kind of stuff, right? My temperature is, my humidity is. Uplinking very small snippets of data over really long periods, really long distances and really low power is a great thing to have. So you can have many, many devices that are all talking LoRa, that are all uploading information and sending it out into the world, and then just one gateway. And that gateway might be receiving data from like 100 different sensors and bringing them all together. Okay. So again, that's stage 2 is obtaining information from our sensors and actuators. These would also be the devices that would send out information. Okay, so if we wanted, if our end device was a motor and we wanted to turn on and off that motor or set it to a certain speed or whatever, it would be attached to our network and it would have a address. It would have a unique address. And we would go, hey, motor AB619, turn on, right? And then it would get the packet. It would go through this whole chain, the rest of it that I'll explain in a second. But at some point, our gateway would broadcast the signal that was meant for our end device, whatever address I just said, that it would be listening for and could turn on or off or do whatever we tell it to do. All right, so from my own experience, this is where my role ended. Once information was kind of in the wall, so to speak, it was in a cable going up to the internet service provider, it was out of my hands. It was time for someone else on the programming team or the sales team to work on the back end, on the server side, and really start to move that data around. Okay, now you have it digitized, we have it maybe in a database somewhere. What do we do with it? And how do we shuttle that information to get it into people's iPads or to actually present that information in a useful format? This still continues to be network architecture. We are the third stage of the third layer up in this scheme. Okay, so now we have devices. Those devices are talking to gateways. Those gateways are talking to servers. Okay, and the servers have a whole bunch of stuff going on. They might be storing that in a database for later, right? Like tracking history over time, for example. It might have a front end that it's presenting users, or an application, we call it. Okay, there's so much code that has to say, okay, now that we have this information in this database, here's how you show it in a graph or a chart or a document, right? That something has to do that and serve it up onto a web page. That's the application. We also might have one or more utility servers. Okay, where we're sending or receiving data to other programs or other services that you could kind of patch into on demand. Okay. So this is our third stage. Actually, it's just our application, our edge server. This is where we can do certain things with our information. We can trigger alerts. We can do end devices. So your server might go, if a device temperature is high, turn on a fan, and that might be a different device. So one device might be a temperature sensor, one device might be a fan, and the thing that links the behavior of the two is our application server, right? So this stuff, everything that lives outside of our server but still talks to it, lives in a data center, right? It lives at Amazon, or it lives at Microsoft, or it lives at Google, okay? So these are also managed, and also it's someone's job to create this architecture. How exactly are we storing this information? Where exactly are we storing that information? For example, there's something called in Amazon, which is called AWS. There's something called an S3 bucket. Okay, it's a very interesting concept that I learned pretty early on, that it really is a data bucket. You can stick photos in there, you can stick text in there, you can stick any arbitrary data, and then pull it out for any arbitrary reason forevermore. Okay, and so this bucket has to be set up and configured and managed, and there's a web portal for it, right? It's a whole ass job to maintain that database and to look it over and to string it all together. Okay, so it's very interesting when you keep in mind the complexity of all of this, right? As we start from this little itty bitty piece of data, and then it gets wrapped in all this complexity. Okay, and that actually is more or less how packetized communication works. That's a good segue. Yes. Nailed it. Okay, so the really interesting thing is that when we send information out into the world with a computer, we are wrapping it. Okay, so first we have our data, right? It's really simple text data. It might even only be a few bytes big, okay? But then we wrap that data in a header packet, right? What this is, where it came from. Our application layer is the actual data, right? The stuff that we're interested in. If we're in a video call, this is like a frame of video data, for example. Transport layer is where we're starting to wrap that data in other information. Where did it come from, source IP, where is it going to, destination IP, how much data is it, how large is the message, all that stuff. Okay, that gets wrapped in information. It gets wrapped once more, and even more information that's critical for the internet to know in order to route it correctly. And on and on and on, we keep adding envelopes over our data. But an interesting thing happens is that once we set it through, the pipe, so to speak, those layers start getting peeled off, because inside of each of those layers is where it's coming from and where it's going to. Okay, so if we have a device that, give me a second to draw this network. Okay. So if I have a device, if this is my starter device, right, my source device, that source device will send or have its information be encoded kind of like this. This isn't an exact explanation. I'm just kind of hand waving how IP addressing works. Okay, but the idea is that this is the first tier. This is the identifier for the lowest tier. Okay, for example, there might be two choices on this bottom rung for what identifies this computer, the source of this information. Okay, and it might have two choices. Are we device 0 or are we device 1? We are device 1, so we put a 1 here. Then we go up the chain. Are we device 0 or are we device 1? We're device 1, so we go up the chain. Okay, so we can get a specific one. Now you can imagine that if this isn't a choice of 1, but it's 255 different choices, okay, now we start to see where actual IP addresses come from. Where each of these is up to 255, each of these is 255, each of these is 255. Okay, so it dials down where the biggest number tells you what trunk you're on, the next biggest number tells you what branch you're on, next biggest number tells you what twig you're on, okay, until you dial down right until your computer. Same deal for getting to where you're sending that data to. Okay, this server has the same deal, right? It's at the end of a branch, at the end of a twig somewhere, at the end of some tree, okay? So if we send the information from here to this trunk, to this branch, to this twig, right, to this leaf, then it will arrive at the other end in that kind of fashion. And the way that we do that is by literally wrapping the message in layers that come off as it goes through that process. So we add a layer, we add a layer, add a layer, we subtract a layer, we subtract a layer, we subtract a layer, and then it goes there. Does that kind of make sense? So that is, again, a hand wave explanation. You can have an entire class on networking and how TCP works. Even like a 5 or 10 minute YouTube video would probably do it more justice than what I just did. But I wanted to introduce the idea of addressing and the idea of networking. Okay? All right, so here is, again, more nitty-gritty of how different tiers talk to each other, okay? Because not only might we have different information exchanging, you know, like I said, this is the branch and this is the tree, but this branch might be Wi-Fi, but this branch might be Ethernet. Right, that the protocols or the languages might change when we go from one layer to the next layer. Okay, that data might be really raw information at the lower ends, you know, ones and zeros, but towards the upper ends, we're really talking about packets of information or, you know, kind of higher orders of information, if that makes sense. So don't really worry about the bottom layer here. This is the standard. These are documents that kind of describe if no one came before us. Okay, how do you make a Bluetooth radio? That is defined by this standard. Okay, what frequency you're on, you know, how bits and bytes work. Okay, the next step up is the physical and data layer. Okay, this is getting information from point A to point B physically. Okay, wiggling a wire that is connected to other wires galvanically is a physical method. Okay, that would be like Ethernet or serial, right? TTL, the actual physical movement of electrons. Okay, and that might be done through a physical property protocol, LAN, Ethernet, or wirelessly through different protocols, Bluetooth, cellular, GSM, Wi-Fi, again, Ethernet, physical, or you know, different more niche communication technologies like RFID, NFC, right, is also technically a wireless communication protocol, all that good stuff. Okay, so once we have that information, this is where we start to packetize that information. So it goes through the IP, TCP IP network, where it gets addressed, right? That information gets a to and from marker put onto it, and then it actually gets transmitted, okay? And then even on top of that, we have higher order protocols, HTTP, MQTT, which we'll go over in a second, that says essentially like how that data is pushed and pulled, that it is an even greater form of regulation on how information is posted and retrieved. Okay. All right, so like I said, each one of those bins, each stop in our service architecture could really blow up in complexity. We could take a look at each one of those blocks and we could explode it into an even more complex system. This is the step that I was talking about that came like just after my involvement, where we now have data in the cloud. It is up on an endpoint somewhere, and it is up to the programmers, the computer scientists, the big data engineers to actually work with it. Okay. So typically what happens is that the data would get stored, and it would be stored in a bucket of some kind. Okay, so like your Amazon S3 bucket, okay, your, I forget what it is for the other ones, I've really only worked with AWS, but you'll have your data stuck somewhere, and then you'll have rules that work with that data, right? It'll refresh, it'll check, what the current status of that data is, and then it'll do something to it every so often. It'll generate reports, it'll check to things, see if things are over threshold to issue alerts, right? Your application will be running on this server somewhere in one or more places, really. You probably have a website running on here. In addition to your database manager, you probably have like messaging, aside from the actual thing that is pushing and pulling messages besides. Okay, but all that stuff would live on the back end, on the cloud probably, that you would have a server that would just be virtual, that you would have a program running on, that you would have your data sent to. Okay, so the gateway, the end device is addressing, hey, I want to send my information here to this address. Okay, that's how it gets to a certain point on this network. And then depending on our application, one server or another, we would change this IP address, or we would change this as endpoint accordingly, so we're sending information to the right spot. And then the server would just know that information that came from device number whatever meant something, right? It would know that it was a pressure sensor or a temperature sensor that was deployed in Arizona or whatever. It would, have meaning to it. So this is just a little bit going into this packetizing that I was talking about here, where we have our data, right? The thing that is actually important to us, the flow rate, the presence or absence of something, the ones and zeros of it, that actually represents surprisingly little in our total payload, because piled on top of that is all the other stuff that we need in order for it to get through the right place when going through the network. Okay, so this is literally what the ones and zeros of a TCP IP network packet looks like. Okay, it's like the version of the protocol that we're using. Let's use the same version of English, not Old English, New English. It's a heads up on how big the packet is, right, on that packet length. What kind of packet is it? Here's our checksum, so if a solar flare or something mangles our signal, a 1 gets bit flipped into a 0 or a 0 into a 1, this checksum would match or not match. If it matches, we know we're good, and if it doesn't match, then we just toss it away or do something different. Here is our source and destination address. Again, this is kind of our to and from on our letter. and other options and padding to make sure that it is the right size that it expects. So we pack all that information up, we send it out, and then each of that information peels off as we go through. It checks the destination, it checks the type, it checks where it came from, and then it shuttles it accordingly until at the very end, really all this device sees is just the address, where it came from, and the data inside of the header. All right. So we brought up Modbus before, and we're going to go over it again. I'm going to see if we can do Modbus for our lab, but it might be too advanced for this class. So I'm not sure if we really are going to do PLC to PLC communication in this class this time or not. Just a heads up. But this stuff will still be good to know. All right, one thing that we talked about before is that Modbus, the really great thing about Modbus is that it lets us share lines. Meaning that if I have one PLC, okay, and it takes 3 lines to talk to another PLC over Modbus, right, that's actually the 3 lines, the 3 ports on the front of the PLC device, your Modbus. We don't have to have 3 more lines and 3 more lines and 3 more lines, 12 lines if we want to talk to 4 more devices. We can just keep daisy chaining along. That one talks to that one, 3 more lines, talks to that one, 3 more lines, talks to that one, right? Technically, this is a form of networking. It's pretty lowbrow, but it is useful and it is technically networking. Okay, the thing you want to know is that there's even addressing in here, because we have to say, hey, PLC number 1, do the thing, or PLC number 4, do the thing, and PLCs 2 and 3 would not do the thing, right? So for that, we have addressing, where this would be, address 0, 0x0, this would be address 1, 0x1, this would be address 2, 0x2, and 3, 0x3. So we go, hey, device 0x3, divulge information in register 4. It would go, yes, boss, and it would shuttle up that data. Okay, that is serial or RTU. Okay, that's where we have our A line, our B line, and ground. Literally just 3 copper wires that's needed for that. Okay. TCP needs a whole lot more than 3 wires. A TCP actually uses Ethernet. Okay, so it uses the Ethernet jack. That uses different protocols. I'm pretty sure that uses A plus, A minus, and B plus 2 twisted pairs at the very least, and ground. Okay, so more ports besides, but pretty standard jack, right? You can just get an Ethernet cable, one side goes to the other side and plug it in, and you're good to go. You don't really see all the different conductors. There's like 12 or 8 or 12 different conductors, different copper wires inside of an Ethernet cable, but you'd never really know, right? Anyway, this networking is done in a slightly different fashion, okay, where we're still going through an Ethernet switch instead as our main device, and then we were all talking to the Ethernet switch. Okay, where even if we had like a master device over here, a master PLC, we would all be on this Ethernet, what would you call that? Ethernet switch port to talk to our other PLCs. Okay, so networking is done a little bit different in that way. All right, some pros and cons that are worth remembering that will impress a future boss one day, that you know what Modbus is and what it does and what it's good at and what it's bad at. I'm going to read from the slide a little bit. I hope you'll forgive me because I don't typically do this. But for Modbus, okay, this is where those protocol types, the actual data exchange. So we're talking serial, RS-485 or RS-232. You guys remember what those are, right? The differential data protocols, the A line and the B line that goes high or low. That's our RS-485 or RS-232. The network topology, the layout of the network is typically daisy chained, just one leading into another, leading into another. Maximum range is, of course, is essentially limited by our protocol. Our differential, how can we tell one bit from another bit? Around 4,000 feet is when we start to struggle to make the net differentiation. And we can only go so fast, we can only wiggle the wire so fast before we lose track of state changes. And that's around 38,000 times per second that we can send a signal change. Okay. Simpler devices typically use these, like pressure sensors, flow meters, gas analyzers. Simple cases typically. And then this would be the topology that they were talking about, where we would have one device, one PLC that's our Modbus master, and then we would have one or more slave devices that would either be sending data to, right, or we're braiding to. For example, if it's an actuator, go this way, go that way, stop, start. Or if it's a sensor where we might request information, we say, hey, sensor 2, what is information 1? And then it kicks that back to our master. I'll tell you a little bit more about that in a second, because Modbus is a PLC thing. PLCs are used very extensively for Modbus. Okay, it's like one thing that they really jam at doing. They're very, very useful for doing. Okay. The other thing, and why our devices have Ethernet ports on them to begin with, right? Almost every PLC these days has an Ethernet jack on it, is because we can put data over that line through Modbus. Okay, so that's done with Ethernet as the communication with RJ45 connector. Okay, network topology is not necessarily daisy chain. Okay, because we have a gateway. Let's work a second ago. Because we have a gateway in the mix, this is our Ethernet port, right? Our Ethernet switch. This is star topology, where our master is here, and then it would radiate out kind of like spokes on a wheel. Okay, that's star topology. For each of these would be our end sensors that is connected by a common hub, which would be our switch or our Ethernet port. Okay. Daisy chaining is when we go from one into the other into the other. Okay, so if we want to talk to this device, information would have to pass through these first two devices. Okay, this is the way that this is typically done. Is that if we are talking to or addressing this device, we send data to all devices. They can all hear all the information, but they only care about when we say their name. Essentially, they don't perk up and start paying attention until we address them. So they just ignore everything else unless they're addressed. Okay, Modbus TCP is definitely faster than Modbus RTU. Okay, this serial type is, when we're talking about baud rates, that's like dial-up rate that we're talking about. We're talking about kilohertz or thousands of times per second. But Ethernet, we're starting to get like gigahertz, right? Like millions or billions of times per second that we can change the signal. Okay. This is often like higher order PLC to PLC communication. Remote communication, like if you have a control room that is in a different state, you would have that networked through Ethernet to other devices, for example. People are blowing up my phone. Okay. MQTT is a bit niche, but again, I wanted to let you guys know about this because it is a messaging protocol. So the idea is that, okay, we're moving really small amounts of data, but it takes relatively large amount of data to get that data from point A to point B. You know, there's all that addressing, there's all that to and from, and all that other stuff that has to go on top, and it's such a complex process just to handle data from point A to point B. How do we do that as streamlined as possible, involving as little processing as possible, all that good stuff. So MQTT was born. The way that MQTT works is that you have a central server called an MQTT broker. Oh, come on. Never ends. That we send and receive information to. Okay, we'll have a list of devices and a list of things about each device. So I'll have device 1, and that device will have a temperature, it'll have a pressure, it'll have a battery level, whatever. Okay. And the device, every time it publishes every time it writes a new message, it updates each of these little bits of information. What is the current temperature? What is the current pressure? What is the current battery? It publishes a message that just updates one little part of that. It goes, my current moisture rate is this. My current temperature rate is this. And it does that at whatever rate it wants, once a minute, once an hour, whatever. And then, periodically, our application server, right, the thing that's actually running our website or our mobile app or whatever, would periodically either give actions, open the thing, close the thing, or query data. What is the current status of device 1? And then it would rattle off the temperature is this, the pressure is this, the battery is this, and so on. It's a way we organize and transmit data from our really small edge devices. These are our ESP32s and our Raspberry Pis and things like that. And how do we get that really leanly into our big hefty cloud server as simply as possible? And the way that can be done is through MQTT. There's definitely more ways to do this, but this is just one of the standardized protocols that enables that kind of communication. Okay. Here we're going to talk a little bit more about Modbus. Okay, again, one of the powerful parts of Modbus is that it lets us do simple networking between devices. Okay, so we can have, in one big facility or one big factory, we might have lots of different things going on, temperature sensors and controllers, robotics, pumps turning on and off, even just the lights. Okay, each of those would probably be controlled by a specific controller. It's highly unlikely that you have one computer that's spidering out to control everything, right? Because then if your lights go down, your pumps go out too. Not ideal. So instead you might have a master controller that lives in your control room that would talk to several more controllers that are ultimately in charge of each of those subtasks, right? And then each of those would talk over Modbus, that is the language that we're talking to say individual pieces of information. So each of these end devices would kind of be like a book or a chest of information that it's constantly updating into that chest, based on what its current sensor value is, but we still need to open that chest once in a while to see that information, to grab the current information out of there, okay? So the way that we do that, the nitty-gritty of how we do that is like so. Okay, so this, when I was talking about that it's a book, inside of our device, so a device might be address 0x0, right? The 0th device, the first address on the bus. And then that address will have even more addresses, more slots for data to go. Okay, and each of these data slots can hold some amount of information. Okay, here this is 8 bits. Okay, so that's like pretty much one number you could put in there. So this is a number. This might be a number. This might be a letter, A, B, C, D, E, F, G, right? One piece of information that you can store in 8 bytes. So this would be address 0x0. This would be address 0x1. This would be address 0x2. Okay, imagine if we had a flow rate sensor, a flow meter that was on Modbus, that talked Modbus. Okay, that flow meter might have an identifier, is very common, a number that we expect. So if I read this register, it's called a register. If I read register 0x0 and I get back 0xAF, I don't remember what decimal number, but that's a specific number out of 255, right? One specific combination that is possible out of all combinations. And this could be a good sanity check that when I first talk to this device, I go, hey, flow meter 1, flow meter 2, give me information that's in your first register, that's in register 0. And if I get 0xAF, I know I'm talking to the right device. If I get anything else, then something else is up. I'm talking to the wrong device, there's a networking issue, whatever. And then it continues from there. So each of these pieces, each of these registers, these slots of information, will have something in here. And each of these slots, by the way, is completely arbitrary. Okay, these slots is Modbus. Modbus provides this kind of organization that we can stick data into here and read data from these registers. That's kind of like what Modbus is as a protocol. Okay. What actually is in these arbitrary, holders of information lies in the data sheet. It's the person who made the device that decided what register 0 means, what register 1 means, or what register 2 means. Okay, so in a flow meter, for example, register 1 might be like liters per second. Okay, so the number that's in this spot is the sensor data. Okay, this one maybe might be like an error information, where if this is anything other than 0, then we currently have an error going on. Okay. So what my master controller would be doing is for every one of the devices that's on the bus, it would be querying the piece of information that matters to it at any given time. For example, if we first online the system, the master boots for the very first time, it might check the identifier. So it would go, hey, flow meter 0, what is in address 0? And then it would say 0xAF, okay? And then maybe every 10 milliseconds after that, in our fast task group, we might ask, hey, flow meter, what at this instant in time is your current flow rate? So it would go device 0, address 0x1, what is it? And then it would spit out that information over the line. Okay. So that's what we're seeing here. So this is a actual Modbus device, an actual data sheet component, and it's telling us what is in each and every one of these data sheet slots. So here, an address 0x001D, address number 30, I think that's 30 in decimal. Okay, read or write, right? So for example, if you write to a register, if I had a robot arm that was controlled by Modbus, I might say register 4, if I write a 1 in that register, it should move to the right position, and if I write a 0, it should move to the left position. And that's one way that you can control the arm, by writing a 1 or a 0 to that Modbus register accordingly. Right? And then the controller that's on that arm would just look at that register over and over, what its current state is, and if it changes to a 1, it would do whatever motor movements it does. It would control, right, the motor controller or the driver to swivel the arm to where it needs to go. Okay, so the way that this is actually done is with codes and the actual data. Okay, so these codes, 1, 2, 5, 15, 3, 4, so on and so forth, is how we actually get the receiver to divulge the information we want. remember, at the end of the day, especially for serial RTU, the 3 copper lines, okay, all we're doing is wiggling those lines up and down, okay? So for a given 8 wiggles, or for a given clock signal, I guess, for when it's low and when it's high, and low again, is what defines up to 8 a byte, right? So this byte, 11001100, 1, 2, 3, 4, 5, 6, 7, 8, yes. So this byte would be a number transmitted in this way, okay? The way that the Modbus protocol works is that we transmit what we want to do onto the line, or actually, sorry, we do the address. Okay, so we give information like this. We give the address, which means, hey, devices, only pay attention to me, to the data after this message if your address matches this. If you are device number 1, wake up and keep listening. If not, go to sleep. Okay, so address 0x00. Now we have our command block. This is, do we want to read? Do we want to write? Whatever. That's what this chart is saying. Okay, just like PLC, we have coils and contacts. Okay, that's what these registers are actually called, is coils when we're storing information. Okay, so we can trigger different codes. For example, if we want to write a single register, we want to change the information that's inside of this register for whatever reason. Okay, we would write code 6, which means that this byte would be 0x6, right? That would be 0000011, yes. 1, 2, 3, 4, 5, 6, 7, 8. Yes, that's 6, okay. Or that's 3. That's 6. Binary, yes. Okay. So, address is the first byte. The action is the second byte. What are we doing? And then the actual register, which one are we doing that to, is the next bit of information. Okay, so if we cared about changing what is in address 45, we would go 0x45. Okay, what it's doing over there is this is a 8-bit number, which means that we could have 0 to 255 different devices, right? Different combinations of zeros and ones. When you have more like this is in hex. This is a 16-bit address, okay? Which means that you could have 65,000 different addresses, right? 16 different bytes, okay? But in any case, this is the register. Okay, and then this might hold arbitrary amounts of information. It might hold a sensor reading. It might hold whether or not to do an action. It's entirely dependent on what that thing is and how they've designed it to work. When we design PLC to PLC communication, we set up the registers too. So you would have a structured text that would set up, this is register 1 and what information goes into here. This is register 2 and what information goes into there. And then that way, when you have one PLC that requests from your PLC, hey, what information is in register blah blah, it will yield that information through software. Okay. Any questions there? Nope. Okay. All right, I think, yeah, almost done. And then we can catch up on labs. So, this is what I was talking about for why PLC to PLC communication can be so cool, is because we can control so many different devices, and we can have such control over system architecture, right? Where depending on the layout of our factory, for example, it might make sense for this one process that has a whole bunch of different actuators and sensors on it that maybe this is a closed loop feedback system, and all of that should be going to just one controller. But in another part of the system, it might make more sense to have a PLC talk to another PLC that's talking to equipment, right? And each of those has its own kind of devices that it's responsible for, or even have just one device per one PLC, depending on what that device is doing and where it's located, and how processor intensive is whatever it's doing, and all that stuff are considerations on system architecture. Okay, so again, it's worth noting that the communication method that is run over these lines would either be our TCP/IP Ethernet network or RS-485-232 for our RTU. Acronyms. Okay. All right. So, Wi-Fi is really interesting in that it kind of skips over or replaces a chain in the network in terms of architecture. Okay, so this is how information actually gets from our device to our digital app, right? So at some point there's the sensor, and then there's the actual microcontroller, and then there's that physical interface. How do we get information to and from that device to talk to our cloud infrastructure and our servers and all that stuff? And the interesting thing is that if you have a device here connected to this device and a device here connected to this device, and you make up your own protocol that bridges that gap, you can pretty much do whatever you want. That as long as data in ones and zeros in here equals ones and zeros coming out of there, that's your physical layer. As long as those are all equal and you're not losing data, you can do whatever you want. That's what Wi-Fi is. Okay? That's a protocol that establishes how we can transmit information wirelessly from one end to the other, and really not have to worry about anything up the chain. All the networking and higher order, like packetization and all that stuff, Wi-Fi doesn't actually care about that. It's just sending information and receiving information. What a physical layer is, essentially. All right, talking about strengths and weaknesses of different RF, different ways of getting information up. In terms of IoT, this is all really good stuff. Okay, so for example, Ethernet, some pros and cons. Pros, really fast. Huge amounts of data can get over Ethernet. It's very reliable, right? Unless your power goes out or if someone cuts a line somewhere, you're unlikely to lose your Ethernet connection. Okay, cons, it's expensive to establish, right? If you have to run or connect 2 points that are a mile across, you have to buy and run a mile of cable. Considerable cost. You have to maintain it too. And the physicality is definitely an issue, right? Whether or not you can actually install it in your factory without blowing holes through walls to route wiring, or to potentially, have trip hazards going on for your workers, is definitely something that is a downside. Okay, Wi-Fi. Something you guys need to know about Wi-Fi is that Wi-Fi is a 2.4 gigahertz frequency. Well, actually, it's either 2.4 or 5, but I'm going to tell you something interesting about that too. Okay, 2.4 gigahertz is a quite high frequency. Okay. LoRa and cellular in the US are approximately 915 megahertz. Okay, to put that into perspective, that is 0.915 gigahertz. Okay, Wi-Fi is great because it is still really fast. We can get huge amounts of information through it, but it is a high frequency RF signal. What that means is that it easily gets blocked by solid things like walls and water and people. Not ideal. Metal, especially. Okay, the explanation that I got that has lived with me is that a higher frequency signal, right, higher frequency means more packed waves like this, as opposed to a lower frequency signal that looks like that, right? If I have a high frequency wave that's traveling through my solid wall, it will spend more time, more oscillations within that wall, as opposed to another signal of the same intensity, right? Maybe the same amount of energy went into emitting both of these signals. But what's going to happen is this one will still be higher intensity coming out of the wall than this one. The frequency will stay the same, but it'll be much weaker. It'll be attenuated. Okay? Because in my headcanon, that it spent more time in the wall trying to vibrate, and by the time it got through, it's weaker. I don't know if that's how that actually works, but in practice, it's definitely true that a higher frequency signal is impeded, is disrupted more by solid structures, by water, things like that, than a lower frequency one. Okay. So this is where another one of our methods comes in, LoRa or cellular, right? They use 915 megahertz, a lower frequency. So it's much easier to get longer distances. Okay, the downside though to LoRa and cellular is that less information per second is able to be transmitted. Okay, we can get a lot of it through LTE and stuff these days, but compared to Wi-Fi, especially 5 gigahertz Wi-Fi, it's quite different. Here's where I'm going with the 5 gigahertz Wi-Fi. Nowadays we're seeing lots of 5 gigahertz devices. 5 gigahertz is excellent for, again, more information more quickly. Great for high quality video and things like that. But again, it gets disrupted by walls twice as much. Okay, it's twice as high frequency, 5 gigahertz versus 2.4 gigahertz for traditional Wi-Fi. Meaning we can carry more information, but it gets disrupted more. So if you are in the same room as your sensor or as your gateway, it's much better for 5 gigahertz than if you wanted to talk to a device that was like across the compound, in a different room entirely, all the way over here, because it would have to travel through many walls and concrete and all that kind of stuff. Okay, so different radio frequencies, different radio protocols can also affect this, right? Some ways that we emit RF are better at, they hedge their bets in more data throughput and less, signal reliability, or more reliability and more distance for less data or less throughput. Okay. The amount of power that it takes to push that signal is also a consideration. Okay, Wi-Fi and BLE, or Bluetooth Low Energy, believe it or not, are still technically both 2.4 gigahertz. They use the exact same frequency. The only thing that's different is the protocol, is the language that they're programmed in, so to speak. BLE is excellent for low power, low data rate exchanges. Okay, so that's where the same frequency but we're optimizing different parts about the signal, but we're using the radio in a slightly different way. So BLE beacons are something that are very common in industry. So they are very small edge devices, sometimes as small as a coin or powered by a coin cell, and they would have very simple sensors on them. Again, like pressure sensors, temperature sensors, really low power stuff. And there would be many of them scattered, hundreds, thousands, through warehouses or through whatever, tracking the situation, the environment on the site. Okay, each of those devices alone can only talk BLE. They can only jump short distances one to the other. So they can't talk to the internet directly. But if you have some gateways scattered around that are in sight of one or more of those sensors, you can use that gateway to jump that information up instead, where that gateway would have both a either Wi-Fi or Ethernet and BLE sensor in there as well, so it would turn BLE information, right, communication into LAN communication that goes up to the cloud. Okay. All right. Yeah, so last one is LoRa. I skipped ahead a little bit, but used very often in industry, agriculture, lots of things where if you need something for the last very, very long time, be very energy efficient, but it needs to cross very large distances, and that distance isn't otherwise covered by traditional cell networks or Wi-Fi or whatever. You could kind of create your own little mini network in a way to transmit that information directly that way. Okay, and that's the end of my lecture content. Anyone have any questions on what's in there? Nope, all good. Okay.